Alright, now let's move ahead and let us study the intersection of a line and a hyperbola. So suppose that we are given the equation of some hyperbola in standard position, that is x square upon a square minus y square upon b square equal to 1, and we are given a line, right, like this. So how do we know whether the line is a secant to the hyperbola, that is it cuts the hyperbola in two different points, or whether it's a tangent to the hyperbola, that means it has only one point in common, or it is neither of them, that means it neither cuts nor touches the hyperbola. So these are the three possible cases. Now here I have shown one case where it is neither touching nor cutting. Another possibility is like this, it is a secant, or there is another possibility, that is it is a tangent. Okay, so it could be a secant, a tangent, or neither of them. Right. Now how do we know, or how do we find out what is the situation? So let us see what to do for that. Let us consider that the equation of the line in its slope intercept form is given to us, that is y equal to mx plus c. Now to find where they intersect or touch each other, basically we have to solve the equation of the hyperbola and that of the line simultaneously, isn't it? So therefore what do we do is we substitute y equal to mx plus c in place of y in the equation of hyperbola, correct? So therefore let us do that. So I have written mx plus c in place of y. Okay, so let us simplify this. Cross multiplying, we get b square x square minus a square into, now mx plus c the whole square is m square x square plus 2mcx plus c square, and right side will be a square b square, which is a common LCM taken to the right. Now let's bring all the terms on one side and collect the x square term, x term, and constant term. So therefore we will get b square minus a square m square x square, correct? It is the x square terms. Then let us collect the x term, which is only one term here, that is minus 2 a square mcx, and then let us collect the constant term. So a square b square is brought on the left, and that is clubbed with minus a square c square. So here we have minus, we can write into bracket a square c square plus a square b square equal to 0. Right. So this is a quadratic equation in x, and clearly based on the nature of the discriminant, that is delta of this equation, we will get the different cases. So if delta is greater than 0, that means we get the roots which are real and distinct. That means the line cuts the hyperbola into real and distinct points. That means clearly the line would be the secant. If delta turns out to be 0, that means we know that the roots of the quadratic equation are real and equal. So geometrically it means there are 2 points but they are one and the same. That means it is a tangent. Only one point effectively is can be seen to be common between hyperbola and the line. And lastly, if the discriminant turns out to be negative, that means the roots are imaginary. So geometrically it means we can't see where it cuts because it's imaginary. So it is neither secant nor tangent. Okay? So in this way we can decide what is the association of a line with respect to a given hyperbola. And based on this we can derive what is called as the condition of tangency. That is, we can get a condition which will tell us directly whether a line is a tangent to the hyperbola or not.